So we start with the Boyle's law, Charles law, and equation uh, equation related to each. So this is basically the chapter 18 that deals with thermal properties of the metal. Okay. So in Boyle's law, this basically deals with the relation between it gives the relation between and pressure and volume of gas, but we have to keep the pressure constant. Okay, sorry, keeping temperature constant. So along the axis X, we plot the graph of 1 over pressure, and and along the axis Y we put the volume. Okay, so this means if we plot this, then we get a straight line. So this gives the idea that pressure pressure is inversely proportional to volume at constant pressure, at constant temperature. Constant temperature. Okay. So this can be written in many forms. So for example, this gives the idea that P times V equals constant. This means we can write this as, if pressure is P1, V1 equal to pressure P2 and V2, and it keep going like this. So this means the product of pressure and volume remains constant always in the Boyle's law, but you have to keep the temperature constant throughout this. Okay, so this is the Boyle's law. Similarly, we have the other is the Charles law. In Charles law, it gives the relation between volume and say temperature, but we have to keeping pressure constant. This means you can see in the plot along the x-axis we plotted the temperature, but be careful, temperature should be in Kelvin scale. Kelvin scale, and along the axis y we plotted the volume. Okay, so if you plotted this, we get a straight line. So this means volume is proportional to temperature, but be careful that this temperature should be in Kelvin, should be in absolute scale. Absolute scale. This means we measure in the Kelvin scale. Okay, so this gives the idea that always V, the ratio of V over T is always constant. Okay, this means this is constant, but we have to keep pressure constant throughout the system. So this gives the idea that the ratio of V1 over T1 will be equal to V2 over T2, and it gives the idea of V3 over T3. It will be keep going like this. So these are the Boyle's law and Charles law. Next, we can consider about the mole. Okay, mole is a unit to measure the quantity of substance. Okay, so how we define the mole is the amount of substance that contains as many molecules as there are atoms in exactly 12 grams of carbon C12. So this number, so 1 mole of every substance have exactly same number of atoms or molecules. This number is called the Avogadro's number. So this number is always same for all molecules if you take the 1 mole of substance. Okay, so let's see that number here. So this number is exactly 6 times 6.02 10 power 23 particles per mole. So this means every mole of substance will consist of 6.02 10 power 23 molecules. Okay, so this is the definition of the mole. So mole means, you can see, is mole is the amount of substance that has exactly that number of molecules. Okay, so let's start with uh, some um, some example. Say, for example, molar mass molar mass of oxygen molecule O2. So this is the oxygen molecule. Okay, is roughly, say, it is 32 gram. Okay, 32 grams. We want to find say, for example, 64 grams of O2 equals how much mole? Okay, we want to find in the mole. So this means we want to convert the mass in gram into the moles. So in that scenario, we use the equation N equals small m over big M. Okay, so small m means mass of substance, mass of substance over the molecular weight. Okay, we use this definition to find the number of mole. So here, this N represents the number of mole. Okay, so in our case, you can see we want to find the number of mole. N equals this M, mass of substance that we have, is 64 gram. So we have 64 gram. Okay, and the molecular weight of oxygen molecule is, this is given, is known, say it is 32 gram. Okay, so this means it is 2 mole. 2 moles. Okay, so this means 64 grams of oxygen is equals to the 2 moles. So if you find time, you can watch those videos to get the more insight, to find how we can convert from grams to mole of any substance. Okay, so this is gas law. This is basically the combination of Boyle's law and Charles' law. Boyle's law and Charles' law. So for the ideal gas, we come to this point. Now, if we combine both Boyle's and Charles' law, we get PV is equal to NKT, where P is the pressure. Okay, P is the pressure, V is the volume, and N is the number of atoms or molecules in the gas. T is the temperature. Be careful that, but T should be in the absolute scale. Okay, and this K is called the Boltzmann constant. So it has always fixed value, which is 1.38 10 power negative 38 joule per coulomb. Okay, so this is the number of mole. This equation can be also written as, this is the same equation. They are not different equation, they are same. They are the same equation. This can be also written as PV is equal to nRT. But here, N is the number of mole. So, but here, be careful about these two kind of N. So this little n is the number of moles that we just talked about. Number of moles can be calculated by using relation m equals n times big M. Okay, that we just talked about this thing. So we can use either equation, you get the same result, and these R is called the molar gas constant, whose value is always constant, which is 8.31 joule per mole per Kelvin. Okay, so this concept gives the idea that these results are true for only for the ideal gas. So we wrote the two equations over here. You see that the two equation is, let's see to the next page. Up, um, let's insert one page over here. So we saw two equation PV equals NKT. Okay, this is same as PV equals nRT in two different forms. These are same equation. So, but it's true. This is true only for ideal gas. Okay. So basically, what does it mean by then ideal gases? Okay. So ideal gas means this, we assume, assumptions are this in general, that to have the ideal gas, there should be negligible intermolecular forces. Intermolecular forces means, say we have two atoms over here, one atom is here, other atom is here, just we say atom 1 and this is atom 2. Okay, so there must be force of attraction or repulsion between this. So we assume if this is ideal gas, if this is the gas in a container, okay, these are the atoms or molecules, this is the gas molecules in the container. So we assume that there is very small forces exist between the atoms or molecules, okay, which is not true, but for ideal gas this is the condition. And we assume that there is elastic collision between atoms or molecules. Elastic collision, you know that there will be no loss of energy. So no loss of energy on collision. Okay, so this is the elastic collision, we define that way. Okay, so and third, in general, we assume that the volume of each atom is very small as compared to the volume of the container. Okay, so we write volume of molecule atom of gas is negligible as compared to the container, as compared to the volume of the container, volume of the container. So in this example, if this is the container, its size is very big. This size is very big as compared to the volume of each molecules. So this is the ideal situations. In that situation, Boyle's law, Charles' law is valid, and the combined form, which we call it ideal gas equation, is true only for this equation is true for only for ideal gas. Okay. So if you understand up to this point, I believe you can answer these questions. Okay, so this asking, let's calculate the number of molecules in air that a typical healthy young adult inhale in one breath with a volume of 500 milliliter at standard temperature and standard pressure. Okay, so you know what in my standard temperature and standard pressure is defined to be here it is 0 degree Celsius and the atmospheric pressure. So you know that 0 degree Celsius is equal to 273 Kelvin, and it's a atmospheric pressure means one atmospheric pressure is generally roughly equal to 1.01 or just 110 power 5 Newton per meter square. Okay, if you know those informations, if you know the volume informations, then for sure you can find the number of molecules of air molecules by using the equations that I just showed you before. Okay, next let's talk about the van der Waal equation. Means why we need. So main question is why we need. Why do we need? Okay, main question is the reason behind of needing van der Waal equation is that already in ideal gas law we assumed ideal gas law is based on the assumption. What is the assumptions? That, for example, assumed that it, it undergoes always elastic collisions. We also assumed the particle's volume is very small as compared to the volume of the container. Okay, which is not true. And we are assuming that there is perfect elastic collisions. Okay, so this will be true only under the ideal situation, which is not true. So to overcome those defects of the model, we need the van der Waal equations. So there are some simulations or just picture you can watch how pressure, volume, and number of molecules will affect. Okay, just see one of them. So in this van der Waal model, we assume that the we can compare the size and volume of each molecule or atom with the volume of the container. So, for example, you can see if temperature is 10 Kelvin, molecules is oscillating or vibrating very slowly. If you change the temperature, you know, it, its vibrational motion increases. Okay, you can look at that thing. It also depends what kind of charges we have weak, strong kind of thing. Okay, so this gives you the idea that how the temperature and the charges will affect its motion. And other thing, this just the give picture that tells you that molecules are not rest except at the Kelvin, which is called the absolute zero. Above absolute zero is always moving like it, with a random motion. Okay, so you can play with this. Uh, Next, let's see. So this van der Waal equation basically is going to relate those is going to overcome those two defects. Means now van der Waal equation gives the relation between particles of a fluid, generally say gas, that have a is not a volume is not zero. It has a non-zero volume and there is interactions. So what we are talking about here is that the size of each particles or each atom is not very small. It has some volume. So it's atom 1 and we can say this as atom 2. Okay, so means now in this van der Waal equation we are actually changing the ideal gas situation. So ideal gas relation, we'll have to change it here. So we know that we use PV is equal to, say, for example, nRT for n mole of gas. This is ideal gas equation. Okay, we just saw that. Want to remove those assumptions, we first assume that particle size of each gas molecule is very small. But here we want to introduce the effect of each volume of each mass of the gas particles. Okay. Another is we assumed there is no interactions, but in reality, there is interaction between the atoms. We want to include those. So if you include those things, the equation PV is equal to nRT will be changed like this. P, so instead of P, we have to write P A times N squared over P squared, okay, times, instead of P, we have to write P minus P equals nRT. So this is the van der Waals equation for n mole of gas. N mole of gas. Okay, so here the attractive force between molecules or atoms which are stronger at higher density and reduce the pressure and are taken into account by the coefficient C. So these are the constant coefficient. Okay, and we again see here the other thing is that the volume of the molecule is represented by positive constant P. So we have two, these are the constant A and these two B are the constants. Okay, that takes into account of two things. The each molecule has finite volume and there is a intermolecular force exists between the atoms. So this A and B are constant, but it varies from atom to atom. So this constant is not constant for everything. So the constant A and B are determined experimentally for each gas. Be careful that. So each gas has A and B value constant and it is different. Okay. So let's start with the PV diagram of the for the ideal gas. So in general, PV diagram for ideal gas is called also called isotherms. So you can guess from this term, iso means same, therm means temperature. So same temperature. So it represents the same temperature. So if you draw the pictures, so it looks like if you draw the pictures, it gives you the hyperbola kind of thing. So if you draw P along the axis Y, P along the volume, V along the axis X, then you will get, so for example, say at the lower temperature, it will be say, this will be say this kind of curve you will get, and for other temperatures, you will have maybe this temperature, okay? So say it is the temperature, say T1, P and V curve, and this other graph is for the temperature T2. So this graph represents T2 is greater than T1, okay? So similarly, if the temperature go higher up, the curve will be changed accordingly. So this is the PV diagram for the ideal situations, okay? Next, we have to see how the curve looks like for the real gas. So this is the PV diagram for real gas. Generally we say it's called the non-ideal gas also. So let's see, what does this graph means to us? So let's start with the one of the things starting from the beginning. Let's see. Let's see here. Say we draw the graph. We do the graph of ideal gas. So P pressure is along the axis Y, P is the volume along the axis X. So if you draw the graph, we can find there is slight deviation from the ideal scenario, okay? So we'll see that our graph will be like this part and it will be straight. Then again, it goes like this for a gas, okay? For a given temperature, say it is temperature T1. So what it is telling about this? It's telling that up to this point, it follows Boyle's law, okay? Follows, say, in general, ideal gas law. But at given temperature. So basically, we are talking about the Boyle's law. Here you see that from this point to that point, even though volume is decreasing, so you see in that way, volume decreases, but pressure is not increasing. You see here, pressure remains constant. This means at that region where this line is parallel to axis, where you are here, where we are going to decrease the volume, but pressure remains the same. So for that region, for that region, for that region, this is the region where liquid and vapor phase coexist. Phases coexist. Okay, so this region is for the gas, and after that you say a small decrease in volume will produce you big change in pressure. So this region represents the liquid. This is not a gas. We cannot use the gas law over here. Okay, so this kind of plot we can use for different temperature. So we can draw we can draw a PV diagram for a gas at different temperature. So this is just for the one temperature. If we draw similar kind of picture for different gas, we'll find this kind of curve. So this means this for temperature T1, okay, this curve is for T2, this for T3, and so on. Okay, but one important concept, interesting point is this. Up to this region, okay, it follows the gases law up to this point that I'm showing you. Okay, but up to this point, after that it is not following the gases law. This means this region where these lines are parallel or parallel to the axis x, this is the liquid and gas phase coexist. So we cannot use the gas law over this region. Okay, after that, if you still decrease the pressure, it will convert it to liquid. Okay, okay, so if you keep going to increasing the temperature, and if you plot P and P graph, you see after certain temperature, this temperature corresponding to, we have what we are doing here, we are drawing the PV diagram for each temperature. So draw, so basically this is the draw PV diagram for different temperature. Okay, it is a T1, started with T1, T2, T3, and so on. Okay, so you see for after certain temperature, say it is represented by the temperature Tc, after this temperature, what will happen? If you decrease the volume, say for example, temperature T4, if you decrease the volume, it will not condense into liquid. It always stay in the liquid phase. One of the interesting points is this. So the temperature, this temperature at which after that liquid phase will not exist is called the critical temperature. So critical temperature is one of the important concepts. This means after critical temperature, you cannot get the liquid phase even though you are going to decrease the volume. Okay, so this graph is different for the ideal scenario. In ideal scenario, you can get like always, if you decrease the volume, pressure will increase. But in this scenario, with the decrease in volume, pressure will also increase, but it will not condense into liquid after a certain temperature. Okay, so this temperature after which we cannot get the liquid phase is called the critical temperature. So it is different for different gases. So oxygen has the different critical temperature. Carbon dioxide, CO2 has different critical temperature. So this PPT diagram will explain why this kind of critical temperature exists for the gases. Okay, so just the explanation at lower temperatures means this plot T1, T2 kind of thing. At lower temperature, the curve begins to looks like a hyperbola, just like the PV curve for real gas. The gas is not behaving ideally and may even liquid. Okay, there is critical point. It means critical temperature above which liquid cannot exist. At some sufficiently high pressure above the critical point, the gas will have the density of liquid but will not condense. So, for example, carbon dioxide cannot be liquefied at a temperature above 31 degrees Celsius. Okay, so this is one of the amazing fact people understand very lately. Even though, so means if the carbon dioxide has temperature 31 degree, if you decrease the volume, it will not condense into liquid. Okay, and this critical pressure is the minimum pressure needed for liquid to exist at this critical temperature. Okay, so we talk about at this point. So I will stop here.